Hi, everyone. Thank you so much for joining today. And thank you to the organizers for inviting me. It's really an honor and a pleasure to be here today. Today, I'm going to talk to you about what deep generative models can do for you, opportunities, challenges, and open questions. This work was done in conjunction with a number of extremely talented collaborators, students listed on the top row, and faculty and industry collaborators listed on the bottom row. So this whole workshop is about exploring the ways in which artificial intelligence and machine learning can help inform tasks in the networking space and vice versa. And when we talk about this relationship, three main types of machine learning algorithms are often mentioned. The first type is classification. So can we classify the characteristics of a particular incoming packet to a network, for example? The second type is reinforcement learning. So can we train agents to make decisions in a randomized, potentially adversarial environment to achieve goals like traffic engineering? And the third category is unsupervised methods, such as classification, which can be used for tools like making sense of complex data sets, and or as a building block in larger pipelines involving either of the previous two categories of algorithms. So this talk is going to be about a fourth category of machine learning algorithm that is, I think, somewhat less widely used in the networking community, but I think has some potentially very interesting implications and is good to be aware of. So we're going to talk about first, what are generative models? Why are they relevant now in particular? And how can they be useful in the networking domain? So what are some of the opportunities, challenges, and limitations? So let's get started. A generative model is just a model of the joint probability distribution of some data set. And this data can be high dimensional. It can include things like labels. It can have multiple dimensions. It can be arbitrarily complex. So to give a concrete example, let's suppose that our data set consists of time series. So here we have x0 to xt minus 1. The goal of a generative model is to try to explain how this data was generated. So one really common generative model that's been studied for many, many decades is autoregressive models. And the key feature of autoregressive models is that it says the next time step is generated as a function of the previous time steps, x0 to xt minus 1, plus some additive noise, and the relationship between the next sample and the previous samples is governed by some parameters theta, which are going to be learned from our data. Okay. So this model raises some important questions like, how do we pick F? How do we combine the noise? Why is it the case that additive noise makes sense here? Okay, so this is one particular example of a generative model that has been commonly used, but it's not at all obvious that this is the right way to model data. So generative models in the networking community are typically used in a three-step process. So the first step is that we use domain knowledge to extract high-level insights about our data. So for example, a network engineer or a researcher might say, okay, I know from experience that my data tends to exhibit temporal patterns. Step two is to then design a parametric model to model these high-level insights. So for example, if I know that my data exhibits temporal patterns, maybe a sensible thing would be to model the data itself as a sinusoid plus some noise. And then finally, the third step is to use our data to populate or to learn what those parameters should be. So maybe we learn that theta gives us a period on the order of 1 day. Okay, so our data is exhibiting diurnal patterns. Now, this pipeline has been used in a bunch of papers in the networking community, ranging back many decades. And the pipeline is very useful in many contexts, but it has two key shortcomings. The first is that it doesn't give us good flexibility. So because we're relying on these high-level structural insights from domain expertise, it makes it difficult to extend models to new types of data. So basically, we need to go through this whole process each time. The second shortcoming is poor fidelity. So these models typically only capture the properties that they were originally designed to capture. So like they might capture diurnal correlations, but they're not going to capture other correlations, such as spatial correlations, for example. Okay. So, so these are two of the key problems with classical approaches to generative modeling in general. So this talk is going to be about a new class of generative models that rely on deep learning. And the idea here is really just to take the first two steps of that process and replace it with a neural network. Okay, so now we design a neural network that outputs data of the correct dimensionality, and then we'll use data to populate the parameters of that neural network. Okay, so this approach is nice in the sense that it's a lot more flexible. Okay, so if we don't need as much domain knowledge in order to apply this pipeline to new problem domains. We just need to know enough to design our neural network to, have the correct dimensionality. However, the big question is, can this kind of a pipeline actually achieve the kinds of fidelity that we need? Does it model the data well? And that's kind of an open question, and that's going to be the main focus of this talk. So in particular, I'm going to be talking today about a class of deep generative models called Generative Adversarial Networks, or GANs. And they are viewed as a breakthrough in generative modeling. So whereas prior approaches were likelihood-based, so their training is based on maximizing the likelihood of the data given some parameters, and they also rely heavily on domain knowledge, GANs use a different type of learning called adversarial learning, which I'll talk about in a second. And they make far fewer a priori assumptions, which is believed to contribute to their massive success in generating photorealistic images and videos. So many of you have probably seen examples of faces generated by GANs. So these are all fake people, none of them are real. And this was previously completely impossible with prior state-of-the-art generative models. So GANs really enabled us to make a big leap in the quality of our generative modeling. Okay, so the natural question is, why are they so successful? What is contributing to this success? Well, let's start by explaining how GANs work. So the idea is that we start with a data set that we want to model. Okay, so typically people talk about GANs, they're talking about images. So let's suppose we have a data set of facial images, and we want to train a GAN to be able to produce samples from the distribution of facial images. The way this is typically done is by training one neural network called a generator. And the goal of the generator is to take as input a noise vector, Z, and output a sample of the correct dimensionality. So in this case, it's outputting an image. Now, our goal is to make this generator output faces. So what do? We introduce a second neural network called the discriminator. And the job of the discriminator is to take as input samples, and it has to choose if the samples are real or fake. So right now, the discriminator is seeing a picture from a dog, a picture from the generator, so it should say that that's fake. And if it sees a picture from the real data set, it should output real. Now, these two components, the generator and the discriminator, are trained in alternation until the generator is able to consistently produce images that are fooling the discriminator. Okay? And prior results have shown that if you train a GAN on enough data and with high enough capacity generator and discriminator, then ultimately this will converge to the true probability distribution. Okay, so we have essentially a perfect generative model. Now, of course, in reality, we don't have infinite data and we don't have infinite capacity, so there's a lot of practical problems that are not modeled here, but at least in theory, this is the guarantee. So as I mentioned, GANs have been most successfully used in the image and video domains. So a natural question is, can we use these? Are these useful at all in the networking domain? I believe the answer is yes, and I'm going to talk about 3 use cases that where I think GANs can be useful to the networking community. The first is sharing synthetic data. So as I mentioned, this has been one of the most common use cases of classical generative models, but GANs seem to introduce new possibilities that were not previously possible. The second use case I'll discuss is discovering malicious inputs to black box systems. And the third is making sense of complex data sets. All right, so let me start with sharing synthetic data. Today, a key stumbling block is access to data, or lack thereof. So enterprises often have data that they cannot share with each other due to privacy concerns, which means that collaborative opportunities often go untapped. Even within the same enterprise, different divisions sometimes are not able to share data. So for example, Google Maps should not use information from Gmail. And this is due to privacy policies. This again can have negative impact in terms of the quality of your product. And then of course, way out in left field, we have our researchers who don't have access to any data at all. And this has led to problems of unreproducible research, as well as data-driven research being limited only to those researchers who have connections to large industry. So the situation right now is pretty grim. And an idea that people have long been exploring and trying to evaluate is whether we can use generative models to help with this. So the idea is that different enterprises or different entities who hold data can train generative models of their sensitive data and either share those generative models directly with one another or through a centralized clearinghouse, such as an ISAC or an ISAO. Okay. And the hope is that this would enable more data sharing than is what's currently the case today. Now, what's the problem with this vision? Well, there's 2 main problems. The first one is fidelity. So if I share a generative model of my data, is that actually going to give any benefit to the people who see my generative model? So if the real distribution has certain properties, then the generated distribution should also exhibit those same properties. And the second problem, which is really the motivator for this entire use case, is privacy. So let's suppose I am able to learn a good generative model of my sensitive data. What is that leaking about my real data? And in particular, we're interested in 2 main types of privacy concerns. The first is business secrets, and the second is user data. Both are problematic. So existing methods today on this trade-off curve, we have anonymized raw data, which tends to have very good fidelity, but actually in practice, it doesn't have great privacy. So there have been a number of high-profile incidents where anonymized data sets were de-anonymized using side information. So the Netflix data set is probably the most well-known of these. At the other end of the spectrum, we have expert-designed parametric models of the kind that I mentioned earlier. And these tend to have very good privacy properties because they're not really encoding very much information. But the flip side of that is that their fidelity just isn't very good. So what we've been exploring is something in between, where we're using machine learned models that can be trained with privacy-preserving training methods and hopefully allow us to get a better trade-off between privacy and fidelity. And so I'll be talking about a system that we designed recently called Doppelganger, which was really focused primarily on the fidelity problem, but I'll also mention some of the insights that we got about privacy over the course of this project. Okay, so what kinds of data are we interested in? So with Doppelganger, we were really focusing on multidimensional time series, and these are numeric time series, so things like traffic measurements, with some associated metadata. Okay, So for example, if you're measuring, web traffic from different types of clients, the time series could be the amount of traffic that you're seeing daily, and the metadata could be attributes like the origin of the traffic and the category of traffic, so like mobile versus cable. And we focused really on networking, security, and systems data sets. So we looked at cluster traces from Google and IBM, as well as traffic measurements from Wikipedia and the FCC Measuring Broadband America project. So I'm going to start by explaining to you how Doppelganger is designed, and I'm going to break the design of Doppelganger into 3 parts. So the first part was really designed to enable us to generate time series data. Okay, so remember when I explained how GANs work, the generator is just a neural network. And so if you use a regular feed-forward neural network, it's going to output a signal of a fixed dimension. This doesn't work if we want to produce time series, so instead we replaced that feed-forward neural network with a recurrent neural network, or an RNN. So the top half of this slide is showing you the RNN. So at each pass of the RNN, we can output another sample. And another component of our design is that instead of having the RNN output only 1 sample at a time, we had it output batched samples. So in this case, it's outputting 3 samples at a time. Okay. The next component of Doppelganger's design is that we ran into a problem when we were training on networking data sets in particular. And that is, these data sets tend to have a very high dynamic range across time series. So what I mean is certain signals may have similar max and min values, whereas other signals can have a much larger max or a much smaller min. And what we found is that when you train GANs on these kind of signals with a very large dynamic range, you get a problem called mode collapse. So this plot is showing you generated samples from a GAN that was trained on a Wikipedia web traffic dataset. Okay, so every time series in this dataset consisted of the number of page views to a different Wikipedia article over 500 days. Okay, so what we're seeing here is a collection of generated samples. So here the horizontal axis is the number of days, and the vertical axis is the normalized number of page views. Okay, so we've normalized it between +1 and -1. And the thing that I want you to notice here is that all of these samples have roughly the same shape. Okay, there's some offset between them, but the overall temporal patterns look the same. And this is indicative of a problem called mode collapse that happens often in GANs, which is where you train your GAN on a diverse data set, but it ends up only generating a small subset of your training data. Okay, so basically it gets stuck in a local minimum and just outputs similar samples all the time. So, okay, so this is a problem, and we tried kind of canonical mode collapse solutions from the machine learning literature and found that they didn't really help that much. So what we did was to design a custom solution for this problem, which we call auto-normalization. So in standard normalization approaches, you would normalize by the global min and max over your data set. So for example, if your data set has 3 signals in it, we would take the global max and the global min, and we would rescale everything so that globally the max and min are plus and minus 1, for example. But this doesn't actually help the GAN learn any better because now everything has just been scaled down by a constant. The relationship between the very variable signals and the kind of less variable signals remains the same. So what we did instead was to normalize each time series individually and store the min and max as fake metadata. Okay, so for example, for the black curve, we would store the min and max value, and normalize it to be between plus and minus 1. For the red curve, we would do the same thing, and for the blue curve, we would do the same thing. Okay? So what this gives us is that it helps the RNN generate realistic-looking time series, and it allows us to abstract away or separate the generation of the max and the min values. And what we observed is that by using this auto-normalization, we were able to get a lot more diversity in our generated samples, which is a lot more similar to the real data. So the third part of the design of Doppelganger is dealing with another challenge, which is capturing the complex relationships in metadata. So remember I said that we're trying to generate both time series and metadata. And the problem is that we need to capture these correlations in our generator. So a really naive way of doing this would be to generate the metadata and the time series jointly. So have one big neural network that spits out both. And the problem is that this just really doesn't capture the correlations well at all. So here I'm showing you a histogram of the minimum values. So remember from the previous slide, we said that now our min and our max values are going to be generated as metadata. So this histogram is showing you the min value from generated time series, both in the real data and in the generated data by Doppelganger. And so what we see is that the real data has two modes and also has these tails that Doppelganger just is not able to capture. So it kind of gets the bimodal distribution, but it's not getting the tails at all. So we realized that this is happening because jointly generating time series with metadata is too difficult. And so what we did was to first decouple the generation of metadata from time series and also introduce an auxiliary discriminator just for the metadata. And what we found is that adding this auxiliary discriminator helped us to capture both the modes and the tails. Okay. So putting all of this together, the design of Doppelganger has three main components. The first is that we're generating our time series by taking multiple passes over an RNN that is outputting batched samples. The second component is that we have a decoupled metadata generator, which is fed into a discriminator, as well as a min-max generator, which is also treated as a metadata generator. And in addition, the third component is this auxiliary discriminator that I mentioned, which is only evaluating our metadata. Okay. So what does this architecture give us? Well, to evaluate it, we ran a number of benchmarks, and I think one of the most interesting ones we looked at was autocorrelation. So in this plot, you're seeing the autocorrelation of that Wikipedia web traffic data set that I mentioned earlier. Okay, so here, the horizontal axis is the number of days, is the time lag of our autocorrelation. And the goal here is for our synthetic data to match the autocorrelation of the real data, which is this orange curve. And I want to point out two things about the real data. The first is that it has these very high frequency squiggles, which represent weekly trends in Wikipedia page views. The second thing that I want to point out about the real data is that it has this peak over at like 365 days. And this is representing annual correlations in Wikipedia page views. So people are, searching for New Year's Eve around New Year's Eve every year. Okay, so the first thing to notice here is that Doppelganger is matching the real data autocorrelation pretty closely, which is nice. And this is actually quite surprising. And the reason it's surprising is because this time series has hundreds of samples, which is pretty long for generative models. Okay, so a lot of the generative models that rely on GANs or RNNs or any kind of deep learning typically degrade after a few tens of samples. So the fact that this was able to generate hundreds of samples is kind of surprising. And the other thing that I want to mention here is that this purple curve, time GAN, is the current state of the art in time series modeling from the machine learning literature. And so we noticed that it doesn't really capture either the short-term or the long-term correlations. And so natural question is, why is that happening? And our hypothesis is that because time GAN really wasn't evaluated or designed for longer time series. So if you look at the evaluation in their paper, it's mostly evaluating on time series that are a few tens of samples long. So, so dealing with long time series is a known challenge in the GAN and generative modeling space. And I think this is actually one of the main issues that needs to be overcome for these kinds of models to be useful for networking. So if we try even doppelganger on signals that are thousands of samples long, we haven't tried it, but our current experiences suggest that it wouldn't do so well. So I think this is one of the big challenges. Okay, the other type of evaluation that we did for our generative model, or for doppelganger, was to try it on downstream tasks. So for example, one use case for synthetic data is to use it to train new algorithms. So here you're seeing a plot where we use, where we train a predictor on synthetic data and try to predict cluster job failures from a Google cluster data set. So will this job complete successfully or will it fail? So here the gridded bars represent training on real data and testing on real data. And so the goal is for doppelganger, or is for any of these generative models, to achieve an accuracy that is comparable to real data. So here on the horizontal axis, we have different types of predictive models that we trained. So MLP is just a regular feed-forward neural network. We also looked at naive Bayes, logistic regression, decision trees, and SVMs. And the vertical axis is the accuracy of our predictor. So as I mentioned, what we want is for the bars to be as close to the gridded bars as possible. So the first thing to observe is that doppelganger is doing better than most of the baselines on most of the classifiers. In particular, for the MLP predictor, it's doing almost 40% better than the closest baseline, which was autoregressive models. But notice that it's still not quite at the level of real data. So I think there is still a lot of room for improvement. And there have been some advances in both the GAN literature and the time series modeling literature since we designed doppelganger. So I don't think that this is necessarily a fundamental limitation. But I think the point here is that using well-designed generative models can give us a lot better accuracy than what we're used to seeing with classical generative models. So the second main component, the second main challenge with generating synthetic data is privacy. And there's two main types of privacy that businesses typically care about. The first is protecting business secrets, which are typically aggregate functions of the data. So like how much traffic is a particular company getting per day. This is the kind of thing they often want to hide. The other thing that they may want to protect is user privacy, and this is typically motivated mainly by regulation, though sometimes they also care inherently about user privacy. And here, some of the main tools that have been proposed are differential privacy. So I'm not going to talk too much about this because what I have, like our experiences with privacy have mostly been negative. It's actually somewhat difficult to use today's tools to achieve good privacy. And I want to give you an example of that related to differential privacy. So we tried training doppelganger on using a common differentially private training algorithm called differentially private stochastic gradient descent. So for those of you who are not familiar with differential privacy, the very quick version is that it's associated with a parameter, epsilon, that tells you how private is your model. So as epsilon gets larger, the model gets less private. So an epsilon of 0 is the best privacy you can hope for. And typically an epsilon around 1 is considered a reasonable privacy guarantee. So if you're at epsilon equals 7 or something, that's already considered a pretty bad privacy guarantee. So in this plot, I'm showing you the autocorrelation plots from before, but now we've trained Doppelganger with differentially private SGD in the purple curve. And what we see is that for epsilon equal to about 1 and epsilon equal to about 0.5, differential privacy essentially destroys the utility of the signal. So the autocorrelation completely does not capture any of the properties of the real data. And this was kind of surprising to us because there's a lot of work right now on using DPSGD to train GANs. I've seen a number of papers that use this approach. And I think what's going on is that in a lot of papers right now, that especially those that are using differential privacy to train GANs, the evaluations tend to be done only on downstream tasks like prediction. And this seems to mask qualitative problems in your data that might not be obvious. So for example, we would never have caught the mode collapse problem if we had not looked at the qualitative properties of the data. And I think that in the machine learning community in particular, there's an emphasis on downstream evaluations and doesn't really care as much about like qualitative examination of data. And I think that that may be partially obscuring some problems in current methodology. So figuring out ways to train differentially private GANs is an active research area. There have been other approaches other than DPSGD, but I just wanted to illustrate this one because we've seen multiple instances of it being used in the literature. So I think two of the main open questions in the area of synthetic data generation are, first of all, fidelity. So can we actually model long sequences of data? And as I mentioned, I think there have been some promising developments recently that could enable this. And can we model things like stateful protocols? Like, is there a hope of generating PCAPs, synthetic PCAPs? And the other main question is privacy. So can we train differentially private GANs, or is differential privacy even the right metric? And we can discuss this maybe later in the Q&A if people are interested. Okay, so the next use case that I wanted to talk about was identifying malicious inputs to black box systems. So as we all know, there's more and more black box systems and devices that are proliferating. And these devices have made it much easier to develop flexible networks with lots of different types of functionality without having to manufacture all of your devices in-house. So these include things like IoT devices, servers and routers, control units in vehicles and manufacturing, and so forth. And a common thread with all of these devices is that we don't necessarily have source code, binaries, protocol formats, design docs, etc. So while this proliferation of black box devices has made it a lot easier to build flexible and functional networks, it's also made it a lot harder to reason about the attack surfaces of our networks. So for example, if we have a data center network that's built with commodity hardware, we may not know all of the intricacies of all the devices that comprise this network. And so it may be difficult to understand if an attacker were to send certain carefully crafted packets to our network, would they be able to, for example, cause inordinate delays in certain types of devices like our switches? So the goal of this second use case is really to identify attack packets without having access to source code or a system description. And in particular, I'm going to focus on a motivating example, which is packet classification. So packet classification is a cornerstone of modern networking. So the idea here is that when network functions like switches see an incoming packet, they need to decide what to do with it. And so typically what happens is that this packet gets sent through some kind of internal classifier, such as a decision tree, and matched to some rule, which tells the switch what action to take on the packet. So there's been a bunch of work in the networking community on designing classifiers that are both compact in representation and also having low classification time on average. So a natural question is, can an attacker identify multiple diverse packets, all of which have high classification times? Okay, so what would an attack on this kind of classification system look like? So to give you an idea of the kinds of problems that we looked at, we ran a packet classifier from NeuroCuts, which was a paper that appeared last year at SIGCOMM. This is a tool for generating decision trees for classifying packets. And so here we generated 2,000 random packets, and we passed each of them through one of these decision trees, and we measured the classification time. And we found a distribution that looks roughly like this. Okay, so most of the packets, which we'll call fast packets, took less than 0.03 milliseconds to classify, whereas the remaining packets, we'll call them slow packets, took longer. And so our goal now is going to be, can we generate many diverse slow packets? Okay, so what would it take to create like an adversarial workload that causes these classifiers to slow down inordinately? Now, some common tools for this kind of black box optimization are from the security community, fuzzing, of course, which is heavily dependent on random sampling. But more generally, there's been a number of tools that are used for these kinds of purposes, including Bayesian optimization, genetic algorithms, simulated annealing, just to name a few. And while these approaches have been moderately successful at these kinds of tasks, at optimizing these kind of black box functions, one of the key problems is that they don't really learn very sophisticated models of the underlying black box system. So this is another area where deep generative models might be useful. Okay. So let's talk about what it would take to, or how one could use deep generative models to improve our ability to identify these malicious input packets. So a kind of naive approach of using GANs here would be the following. Let's suppose we generate a data set of random packets and we pass it through our classifier, our decision tree. Some of these packets will take a long time to classify, others will not take very long at all. So we have a set of slow packets and fast packets. And the slow packets are going to constitute a small minority of the total packets, something like 1% of the total. So a naive approach might be to train a GAN from these slow packets and use that GAN to generate new slow packets. The problem is that here we have so little data from the slow packet category that this GAN is not going to learn well at all. It's going to have problems like memorization, so it's going to output just copies of the initial training data, and it's also going to exhibit mode collapse, which I mentioned earlier, where it doesn't output a diverse set of samples. So what we have been working on is something called AMP-GAN, which is a similar pipeline, but we incorporate a feedback loop. So the idea here is to use both the fast packets and the slow packets, and we'll train something called a conditional GAN, which associates with each sample a label, either fast or slow. Now, once we've trained this conditional GAN, we generate packets with a slow condition, and we feed them back through our classifier and use that to fine-tune our GAN model in a feedback cycle. And we call this AMP-GAN. So this figure is showing you what happens when we start with our initial training data set, which is on the top figure. And on the bottom, we have the classification times after training AMP-GAN, and we produce samples using AMP-GAN. And so what we see is that the classification time moves far to the right. Okay, so we're able to generate packets that take much longer to classify. And actually, we found that almost 99% of the generated packets were unique. So it's not just outputting a single bad packet. It's actually finding a very diverse set of packets. And in fact, if we compare AMP-GAN to other baselines of the kinds that I mentioned earlier, we see that if we limit our approach to a fixed number of system calls, so here system calls corresponds to the number of times we can access our packet classifier, AMP-GAN is generating substantially more slow packets than any of the other baselines. So when we have a budget of 2,000 packets, we're getting a 10x jump in the fraction of slow packets compared to the leading baseline, which was genetic algorithms. And when we increase our budget to 100,000 packets, we're still seeing a 2.5x jump over generalized simulated annealing. And I want to point out that we were not able to run Bayesian optimization for 100,000 packets because Bayesian optimization is very unscalable. So it's not able to handle that large, you have to basically invert a gigantic matrix, which wasn't possible for this number of system calls. So, so this is just one example of how GANs can be used to identify malicious inputs to black box systems. I think there's a number of interesting questions here, including, can you generate malicious sequences of inputs? And more generally, can we use GANs not just for generating malicious inputs, but for arbitrary black box optimizations? So for example, Bayesian optimization was used in a 2017 NSDI paper called Cherry Pick. Can we design these kinds of GAN-based pipelines to optimize black box systems better than some of these baselines? Okay, finally, the third use case that I wanted to talk about, this is the most experimental and one that hasn't actually been evaluated on networking data, but I think that it's a really interesting concept and is something that is worth evaluating and exploring. And this is using an idea called disentangled GANs. So what is a disentangled GAN? To start out, let's go back to regular vanilla GANs. So remember that with vanilla GANs, we have some input noise, Z, that gets fed into a generator, and the generator outputs samples. So in this case, we're going back to the facial images example, just because it's easy to reason about. And our samples might have different factors. Okay, so these factors are attributes like hair color, rotation, background, bangs. These are properties that enable us as humans to understand what are the differences in images and what are the properties that constitute a meaningful difference versus a non-meaningful difference. So, okay, so disentanglement is related to how the inputs to the generator control the outputs. So if I were to tweak one of these input noise elements, let's say Z1, it would impact all of the factors in ways that are difficult to predict. Okay, so if I tweak Z1, it might impact the hair color and the rotation and the bangs of my image. So the idea behind disentangled GANs is that we want to introduce some new inputs, let's call them C1 through CK, that control our K factors. So if I tweak C1, the output image should only have its hair color change and nothing else. And if I tweak CK, we should only see the bangs change and nothing else. Okay, so that's the idea. And the thing that makes disentangled GANs kind of black magic in some sense is that this has to happen in a fully unsupervised way. Okay, so you don't have labels. You don't even know what the factors are ahead of time. The factors have to be discovered in an unsupervised manner. Okay? So all of this is done without labels, no supervision. So I'm going to talk about a disentangled GAN architecture that my collaborators and I recently worked on. And these are examples from of what's called latent traversals from the GAN that we worked on. So the idea here, again, is that we have our inputs, our CIs, which control the factors, and we're going to call the CIs latent codes. And then in addition to that, we have the remaining noise dimensions, the ZIs. Okay, and those are just the regular input noise from before. And what I'm showing here is the output of our generator as we alter only C1 and keep all the other factors the same. Okay, so here I'm toggling C1 from 0 to 1, I'm sweeping it, and we see that the hair color of this guy changes from brown to blonde, but nothing else about the face changes. Okay. Similarly, on the far right, we're sweeping C5 from 0 to 1, and we see that this guy basically grows bangs, but no other aspects of the image are changing. His face remains the same, the background remains the same. And in the bottom row, we see a similar thing for a toy data set called D-Sprites. And this is a data set that's generated purely to evaluate disentanglement. But in this data set, images are controlled by 5 factors: shape, scale, rotation, X position, and Y position. And so here, for example, in C1, as we sweep C1, we see that the shape cycles through all of the possibilities, but nothing else changes. So these are examples of what a disentangled GAN can do. And I think one natural question is, how can you actually achieve this? So the approach that we proposed relies on something called self-supervision, which is a hot topic in the machine learning community right now. But the idea is the following. We're going to generate 2 latent codes such that one of the CIs is identical, but all of the other CIs are different. Okay, so for example, let's suppose that we keep the first code, I = 1, the same, and everything else different. And now we generate 2 images such that CI is the same and everything else is drawn randomly. Now, if we show this pair of images to a human and we ask the human, okay, which of the factors was the same, the human can very easily look at this and say, oh, it's the shape. The shape is the same, but the X position and Y position are all different. If we do this with the following 2 images, the human can say, oh, the X position is the same. And here, the human can say, oh, the Y position is the same. So the idea here is to replace this human with a classifier. Okay, so we're going to replace this with what we call a contrastive regularizer, CR, whose goal is to take in pairs of images that are generated by us and predict which of the latent codes, which of the CIs was the same. Okay, so this is a classification task. It's very well defined. And what's kind of surprising is that if you do this, if you train your GAN with this contrastive regularization, you can actually learn GANs that extract these features, that learn the mapping from latent codes to factors in a fully unsupervised way, leading to the examples that I showed you earlier. So just for completeness, the architecture here looks like the following. We have our usual generator, G, which is taking as input the regular noise, Z, and is also taking as input our latent factors, C. And the generator here is producing samples that are fed to the discriminator, as before. We also have a second component called the InfoGAN encoder, which I won't talk about for the sake of time. But in addition to this top part, which is kind of the usual disentangled GAN architecture, we're adding something called contrastive regularization, CR, which is taking these 2 examples and trying to predict which of the factors was kept the same. And our loss function incorporates both the usual GAN loss, which is the first part, and the second part of our loss is the classification accuracy of our contrastive regularizer. And what we show is that by using this architecture, this self-supervision, we're able to achieve state-of-the-art disentanglement scores. Now, this is maybe a little bit outside the scope of networking, but the reason I think that this is really interesting from a networking perspective is that disentanglement is currently a topic that a lot of people are working on in the machine learning community and are kind of scrambling to find applications for. So can we use disentanglement to actually make sense of networking data, particularly in black box settings? So if, for example, we receive black box bit streams from an unknown protocol, can we use that tools from the disentanglement literature to, for example, understand where the field boundaries are and that one set of bits is deterministically governed by another set of bits? So I think that there's a lot of really interesting questions to be asked around applying disentanglement and disentangled generative models to the to networking data sets. And in particular, I haven't worked on this problem, but there has been some work on time series disentanglement in 2004 and a number of follow-up papers as well. And so I think this is a really interesting area and would be worth exploring. Okay, so that's the 3 use cases that I wanted to talk about. So the take-home messages that I want to leave you with are the following. First of all, deep generative models show promise for a number of networking applications. The most canonical one is synthetic data generation, which we've seen for many decades. The second is identifying malicious packets for black box systems. And this, I think, is a newer use case that is enabled specifically by the fact that generative models have seen a big leap in their accuracy and their ability to model unknown correlations in data. And the third use case, which was really more of an idea about a potential use case, is extracting structural insights from data by using disentangled GANs and disentangled other deep generative models like variational autoencoders. So I think one of the messages that I want to highlight here is that it's often not possible to take these machine learning tools, these deep generative models, and just apply them off the shelf to networking problems. So what we found is that we had to actually tweak the architecture somewhat to make them work for networking domains. However, these modifications tend to be a little bit less, they require a little bit less domain knowledge, and they're a little bit more flexible than traditional approaches for designing generative models. So for this reason, I think that there's some really exciting opportunities and interesting research problems to be explored in the domain of applying deep generative models to networking problems. With that, thank you so much for your time, and I'll be very happy to take questions.